Carruba. I'm going to talk about machine learning classification on new asteroid family members. So, asteroid families, as discussed by Dr. Cellino, are formed as a result of collision or rotational favor of a parent body. They are identified as by similar improper element of proper frequencies. A proper element constant of the motion, stable over time scale of a million years. The most commonly used method for identifying asteroid families is the hierarchical clustering method. So the method works like this. First, we check if there are objects that are closer to a parent body, the distance cutoff in this domain. And the distance cutoff is a value that has to be set for each region of the main belt. If a new object is found, the new body is used as a new parent body, and the process is repeated until no new member is identified. So they usually generate diagrams like this dendrogram that we see in the figure, where we have smaller and smaller family that conglomerate up to larger family if you increase the cutoff distance between members. So the hierarchical clustering method was introduced in the early 90s when the number of asteroids with proper element was of the order of 10,000, like in Zappalan 1990 and 95. ACM for a larger database is affected by the problem of chaining. Two near family emerge when halo members are included. Thanks to robotic services like Spike was linear, the number of asteroid families today larger than 700. The number of asteroids with non-proper element today larger than 750,000. So this number is continually increasing. Will increase by several factors of magnitude, several order of magnitude, because of a new robotic service like the large space service in the next years. So this creates problem for the identification of new asteroid, new member families. And to solve some of this problem, we can use a supervised learning algorithm for machine learning. Supervised learning algorithms have been developed in the last years. They are freely available to the scientific community. Given a persisting population, this method uses the known data to predict new data belong, if the known data belong or not to a given group. Okay. Great. So we can have a standalone where we just use a single algorithm for the problem of identifying new objects. Ensemble method can use several algorithms together and combine the result of each single algorithm to obtain a better result. We can distinguish between bootstrap aggregating or bagging classifiers, where the training data is first split into multiple samples called the bootstrap sample, which method is accounted with for with the same weight, and boosting methods, where the training sample strengthen where the method strengthen the data that has the most unclear method. Each method is accounted with a different weight that depends on the accuracy by which the method classifies each single data. So among the standalone methods, we can distinguish the linear regression. Linear regression searches for linear relationship between an independent variable x or input or a dependent one or an output. For a case, the algorithm uses the problem data for the family to train.
Sorry, Valerio, we cannot hear you very well from time to time. Valerio, are you there? I think there are some connections.
Can you hear?
Not very well.
Is now better? Is this now better?
Yes, now it's better. Yeah. maybe you can switch off.
Maximum.
Maybe you can switch off the webcam.
Okay, among the standalone method. What about now?
We can hear something, but not very well.
I don't know now. The methods we have the case based on this closeness. Well, I don't know what else I can do. I'm sorry.
Okay.
Put this to
don't worry. Now we can hear something. Yes. So you can continue your talk. Please try to continue.
If the majority of the closest neighbors belongs to a class, the point is also classified as such. A parameter of this algorithm is the number of close neighbors used for classifications. So we can also have a decision tree algorithms, which are based essentially on several branches. Imagine that you want to decide if you could use a kite. You need the weather to be windy, sunny, and with low humidity. So you need to take a decision over the weather either to be windy or not, sunny and with low humidity. And every time that you take a decision, you go down a branch in the decision tree parameter. So the number of branches that you use is the max depth is a free parameter of the standalone method. You can use several decision tree together using the as an ensemble method. For example, the randomized forest is an ensemble bagging method where you combine several predictions for decision tree to obtain a better final results with the same weight for each model. Extremely randomized tree or ExtraTree are samples data without replacement. So decision tree decision on the state of the data is based on a majority vote among the results. You can have a boosting algorithm which tracks the model that predicted the least accurate prediction and assigns to them lower weights. The final outcome is reached as a weighted average of the outcome of each standalone method. Other examples are the gradient boosting method or the stream gradient boosting method, which are other examples of boosting algorithm. So why this is important for asteroid families and what is the application of machine learning to asteroid family? We can select 21 asteroid family in the inner, central, and outer main belt at low inclinations and use the data from the asteroid family portal of Radovich et al. We can divide these samples into two parts: the object with low absolute magnitude, which are larger and less likely to be affected by chaining, according to Milan et al., and the object with higher absolute magnitude with a smaller object. So using the smaller the data with a smaller absolute magnitude, we can have less problem with chaining. So we can train our model based on the distribution of proper element A, E, and Ni of the training sample. We can use them to predict the membership of the test sample population, which are the new asteroids that are not included, for instance, in a given classification. So we can distinguish between true positive, which asteroids predict to be family members by both the hierarchical clustering method and machine learning algorithm. False positive, which are predicted to be family members by the machine learning algorithm only, and the false negative, which are objects that are family only predicted only by the machine learning algorithm. So we can introduce a few metrics for determining the success of the algorithm. Completeness is defined as the true positive we divided by the true positive by false negative and measure the ability of the algorithm to retrieve the original population of family members. Precision is the true positive divided true positive by plus false positive. We measure the ability, how precise is retrieve families. Low values occur if the families are large members of false positive. And we can combine the two metrics into one, which is called merit or final parameter, which is just a weighted average of the two. 1/2 of the square root of 1/2 of completeness square by plus precision square. So each algorithm may depend on one more free parameter, which need to be optimized. In the k-nearest neighbor, we have the number of neighbor at each point. So we can use the grid search approach to optimize the free parameter, the hyperparameter of each method to best fit the data for each given asteroid families. So what we did was for each study family, we verify which algorithm provide best performance measured by the final parameter or the merit parameter. Overall, with ExtraTree are the best performance for 10 out of the 21 studied cases, followed by KNN with 4 cases and AdaBoost with 3 families. ExtraTree performed better with family with large, smaller population of objects with small absolute magnitude, while KNN is more apt to fit families that are intermediate with small up to 150 members and with relatively less populous membership of large objects. So ExtraTree was the best tool that we have at our disposal. We can use it to update the list of family members. We can divide the sample of proper element in a given region into 2 parts, with the first part going up to the highest number of members in a given asteroid families. Asteroid in this set of proper element will double with 1 will belong to a given family and 0 otherwise. So machine learning can then use this set to predict which of the unlabeled objects are more likely to belong to a given asteroid families. I think it can be used for the cases in which we have new asteroids that are not yet classified, new discovered, but we would like to know if they are likely or not to be members of asteroid families. So we can apply the ExtraTree to 4 asteroid families: the Eckert, which is a relatively small family of 105 members, ANSA with 1,484 members, Eunomian with more than 6,000 members, and Canis, which is a subfamily of the larger Coronis families. So we can, in all cases, we can identify new family members for all the cases, and this is also important for the case of the Carin families, which is located in a dense region of the Coronis families. We also see that the distribution of the new objects, which are in red with respect to black objects, which are the already known members of the families, is very compatible with the orbital distribution of the non-object. So there are methods that we use that we can compute the quantitative efficiency of this method, but I'm not going to go much in detail into that. So I think that there is a lot of time yet, but I think that we can just go to conclusion and go back if there are questions. We selected 21 asteroid family with a statistically significant population of large objects. We then applied 9 different machine learning algorithms and used 3 parameters to characterize the efficiency with which the algorithm identified new family members compared to the results of traditional AGASM. We used Stadalone, Bagging classifier, and boosting method for this purpose. Among the studied algorithms, the extremely randomized 3 are the best performance that we obtained. So followed by the KNN method and the extremely gradient boosting method. So we can adapt the code for the purpose of automatic updating family membership. We tested them with the case of small, medium-sized, and large asteroid family. In all tested cases, the orbital distribution of newly found members is consistent with distribution of previously known objects, and the Python code used for these tags are publicly available at the GitHub repository. We welcome inputs for any way to improve this algorithm. More information on this work can be found in an article that we published recently on Monte Nautilus, and below we can find the link for the GitHub repository for our codes. And I think that's all that I have to say for now.
Thank you, Valerio.